Okay, so now we're up to lecture 25, I believe. Let me have a quick look. Yep, lecture 25. And we're going to look at the relationship between x and y now. So let's start. We'll start by looking at the conditional probability density function. So we've got x and y, two continuous random variables. They've got a joint probability density function, fx of y. And we've also calculated the marginal densities, f1 of x and f2 of y. We're going to define the conditional density of x given y equals y is given by the f of x given y is f of x and y over f2y. So we basically take our joint and divide it by the marginal of the thing that we're conditioning on. Obviously, for this to be defined, we need that the marginal of y is greater than 0, so we're not dividing by 0. The same if we want the conditional density of y given x. Now we could take the joint distribution and we divide it by the marginal of x. So let's start off. We've got one that we've seen before. We've got f of x of y is 2x, and x lies between 0 and 1, and y lies between 0 and 1. The marginal of these we did in the last lecture, so go back and recap there if you don't remember them. We're going to calculate the conditional distributions. So first of all, we want the f of x given y. That is going to be the f of x and y over the f of 2y, which is just 2x over 1, which is 2x, for x lies between 0 and 1. What about the f of y given x? Well, that's also f of x, y, over this time f1 of x, so it's the margin of x, which is 2x over 2x, which equals 1, for y lies between 0 and 1. Okay, nice and easy. Well, let's talk about independence of two random variables. So now we're going to say that we've got x has the cumulative distribution function f1 of x, and y has the CDF f2 of y. And f and x and y have the joint cumulative distribution of fxy. And we're going to say that the random variables x and y are said to be independent if and only if I can write the joint cumulative distribution function, so capital F of x of y, in terms of the marginal of x, the CDF, and the marginal CDF of y. And this has to be true for every single possible value of x and y. And as before, if x and y are not independent, we'll say they are dependent. Also, we can show that we don't have to get the CDF. So let's look at discrete random variables. If x and y are discrete random variables, they have a joint probability mass function, Px and y. And we have the marginal probability mass function f1 of x and the marginal probability mass function of y, f2 of y. Then they are independent, x and y are independent if and only if I can write the joint probability mass function as the product of the individual marginal distributions. Same again for continuous independent, but now we change it to probability density function. So we've got x and y, they're continuous random variables. They have a joint probability density function, fx of y. They have the marginal PDF, f1 of x, and so that's for x, and y has a marginal probability density function, f2 of y. And x and y are independent if and only if you can write the joint probability density function as the product of the individual marginal distribution functions. So we're going to have two examples. The first example where they will be independent, and the second one where they're dependent, so you can see both. So let's start with the case where we have independent. So we've got our function there. If x and y is 6xy squared, x lies between 0 and 1, and y lies between 0 and 1. And if we want to show that they're independent, what we need to do is we need to calculate the marginal distributions, and then once we've got the marginal distributions, look at the product of them and see if it's equal to the joint. So first of all, we've got f1 of x. That is going to be, we take 6xy squared dy, and we're going to integrate out y from 0 to 1. So this is going to be 6xy cubed over 3. So this is 2xy cubed from 0 to 1, which is 2 x. Let's get to the marginal of y. So we want the marginal of y. So again, integrate the same thing again, but this time with respect to x from 0 to 1, which is now 6x squared y squared over 2, 0 to 1, which simplifies to 3x squared y squared, 0 to 1. Remember, this is with x, so we substitute in for x, which is 3y squared. So now let's multiply them together. So we've got f1x, f2y. That is 2x 3y squared, which is 6xy squared. And that is equal to f of x, y. So they're independent. Let's look at an example where they're not. So here we've got fxy, we've got 2 for, we've got y less than x, and both y and x lie between 0 and 1, and we want to show that they are dependent. Same process again. We calculate the marginals, we look at the product, and we see if it's the same. So first of all, we want the marginal of x. So we're going to integrate our function with respect to dx. Where does x go? X goes between y and 1. So we have to integrate from y to 1. That's going to be 2x y to 1, which is going to be equal to 2 minus y. Let me just check my notes. Nope, I've done that completely wrong. Let's start again, wipe that out, and actually think a little bit better this time. So again, we want to integrate our function, but if we want to get the marginal, we have to get rid of y. Let's go and look at y. Y lies between 0 and x. So that's 0x. So this is now 2y. 0x, which is 2x. Now we should get a sense of deja vu as we start to do y, because that's what Jono foolishly did before. That's going to be 2 dx. X goes between y and 1, which is 2x 1y, which is 2 minus 2y. Let's look at the product. f1 of x, f2 of y equals 2x times by 2 minus 2y, which is 4x 1 minus y, which is not equal to 2, which is obviously this is f of x, y. So they are dependent. We sort of knew that. You saw that in the definition. You can see that, there is this relationship between them right from the start. So there's our first look at how we look at two random variables and we look for independence. Next time we'll start looking at expected values. See you next week.